All right, so today we're going to be talking about the divergence of a vector field. First, to get us going, let's just look at the components. So for divergence of a vector field, first we start off with a vector f, or here I'm gonna just list up the components, where we have a function f of x comma y comma z, a function g of x comma y comma z, and we also have a function h of x comma y comma z. And we say that the divergence of f, is the gradient times the vector f. And so what we get is the partial of f over x plus the partial of g over y. Just keep it all together. I should use that f, plus the partial of h over the partial z. And so that's that part. Now, to kind of talk about the characteristics of this guy, let me just move it down. So the divergence is positive when the rate of change is outward is negative when the rate of change is inward and the divergence is incompressible if the divergence is 0. And those are the key things we're going to be looking at. So let's actually do some examples. All right, so if I wanted to find the divergence of this vector f, where we have x comma y, is equal to negative 8xi plus 8y in the j direction, then first we need to find our partials for the f. So for the f function, it's going to be negative 8x, and for the g function, it's going to be 8y. Now, the partial derivative in respects to x is going to be just -8, and the partial derivative in respects to g here is going to be 8. So thus, here, -8 plus 8 equals 0. And if we go back up, we see that it is incompressible. So this is the divergence for this vector. Now we're going to look at another example where we use trig functions. Let's say we have a vector field of x comma y comma z where we have 6x squared in the I direction minus sine x of z in the I plus j direction. Then I'm looking at f. Let's see f here, where we have 6x squared, and then in g we have negative sine of xz. Now here, if I take the partial in respects to x here, then I'm going to get just 12x, and then if I take the partial in respects to this guy, well, really it's going to be in respects to x and z here, then this is going to give me negative x cosine of xz minus z of cosine xz. And so here, just kind of like with the last example, we're just going to kind of put it all together. So we're going to have 12x minus x cosine of xz minus z of cosine xz. So this would be our divergence. Now I have one more example where we look at an electric field. So here, let's say we have a vector E, which is an electric field, where we have position vector r over the length of that vector times p, where p is some constant, okay? And vector r is x in the hand position plus y in the j direction plus z in the k direction here. Okay, so first we're going to find a formula for the div of A. So, sorry, I meant E. So first we're going to find a formula for div of vector E. So, and by doing so, well, let's list out the components of E. So by listing out the components of E, we're going to have x over x squared plus y squared plus z squared p divided 2 in the I direction plus y x squared plus y squared plus z squared p over 2. So in the j direction plus z in the x squared plus y squared plus z squared p over 2 in the k direction. So when we go to compute the partial derivatives for these, we're going to get as follows. I'm just going to do the first one, as you can already get the notions of how the others are going to kind of go. So if we just look at the first one here, then we're going to have the partial derivative in respect to x, where x divides x squared plus y squared plus z squared p2 to equal 1 over x squared plus y squared plus z squared p over 2 minus p x squared over x squared plus y squared plus z squared. Let me zoom out here. P over 2 plus 1. And the same thing will follow suit for the partial derivative in respects to y and z. So here, once I go to take the divergence of e, so if I go to take the div of e, then what I'm going to get is, well, remember, if the partial of y and z is very comparable to x, then I'm going to have 3 of these, which will get me 3 over x squared plus y squared plus z squared p over 2. And then the same thing also goes for this guy. I'll do him in blue, where I'm going to have minus p x squared plus y squared plus z squared over x squared plus y squared plus z squared p over 2 plus 1. Well, here, since we have 2 of the x squareds plus y squared plus z squared, I can cancel out that plus 1. And what we're going to be left with is just 3 minus p all over x squared plus y squared plus z squared p over 2, which, we clean this up, this will just give me 3 minus p over the position vector r, p. Now, remember I said p is some constant, right? So the constant that is going to equal it out to be 0 will be 3. So if p equals 3, then all of this equals 0. And there you have it for the divergence. Thank you.